Okay, so too good to be true. You probably don't understand the title. I promise that by the end, even of the first part, you will understand the title. I even, for the Hebrew-speaking people, I gave a talk at the Israeli Economic Association, the thinking talk, Tuvim Hashnayim min ha'echad. I even found a nice translation. And if you remember Pugi, Tuvim Hashnayim min ha'echad. Never mind, that level for you. Okay. Tuvim, that's good. Okay. Now, much of what I'm going to talk, not much, some of what I'm going to talk is joint work with Phil Rennie, an economist, and Noam Nissan, computer scientist over there. I guess you are going to get this presentation. So if you want something, you click on it and you can get to my webpage.
I should have said all the slides will be posted on the summer school website.
And my webpage is pretty well organized because that's my way to get to things. So I keep. Okay. So let me start with a very simple problem. I'm going to talk about almost as simple as it can be. Okay. Everything can be made complicated, but if we don't understand the simple problem, we are in trouble. So let's start with a very simple problem. We have one seller, just one, okay? Monopolist, one seller. And one buyer, only one, After we know what to do with one, we can try two. But let's do one. But we have K goods, where K may be bigger than one, okay? Or K items. And the objective is a simple, there may be many objectives. Here we focus on one simple objective. The seller wants to get as much as possible from the buyer by selling him the goods. Okay? Sounds like a good objective. Simple objective, as I said. Okay? Now let's put some flesh into it. So the buyer has some valuations for the goods, which I'm going to denote by x1 up to xk, because those are k goods. So it's how much he values, x1 is how much he values good 1. How much he's willing to pay for good 1. You can think of it as willingness to pay. Okay? Now, we are in a very simple case where the valuation is additive. If I get good 1 and good 2, it's worth to me as a buyer x1 plus x2. Of course, everything can be made more complicated, as I said. I'm trying to make it as simple as possible. That's my aim here. It's contrary than the economics approach that tries to make the model as comprehensive as possible. Here I'm trying to make it as simple as possible, and you'll see it's going to be still not easy. As an understatement. Okay. Now, the buyer knows how much the goods are worth to him, so he knows X. The seller does not know X. Well, sorry, I could make it simpler. The seller knows X. Okay? Lecture is finished, yes? The seller knows X. Say, pay me X1 minus epsilon and get X1, get good 1, pay me X2 minus epsilon, get good 2, and lecture is finished. Okay? So, the seller does not know X, but as any good theorist does, he has a probability distribution over that. It's Bayesian.
When you say good theorist,
not that good. As some theorists, okay, may do. The seller has a probability, has a belief over X.
Language comment, I think goods does not have a singular.
it does.
It does?
It does.
Okay, all pun questions at the end. Otherwise, you're not going to finish this lecture. Okay? Should I tell you a story? No. Remind me, maybe in the second part, I'll tell you about. Okay, never mind. So the seller has a probability distribution over X. X is a k-dimensional vector. In RK plus, I forgot to say that values are non-negative. Again, another simplification. So there is some probability distribution, script f on RK plus, which represents the beliefs of the seller on what the possible vectors of valuation of the buyers are. Okay? Now the seller knows f, but does not know x. Okay? The buyer knows x. Very good. So think of x as a random variable. That's the easiest way to think about. So it's randomly realized, There was some geological survey, and if the geological survey came this way, then the first, the oil is worth for me this much, the gas is worth for me this much, etc., etc. If the survey came out differently, then I have different valuations. Okay, now again, we are simplifying. We are assuming that the seller and the buyer have quasi-linear utilities. What it means is, if I get $7, it's worth to me 7. Okay? So dollars are utils. Moreover, if the buyer gets a good that is worth for him 100, and he has to pay 20, his utility is 80. As simple as it can be. Okay? Risk neutral. If I get 10 with probability 1/2 and 20 with probability 1/2, it's like getting 15 for sure. Okay? Everything here can be generalized, but as I said, everything is as simple as can be. Now, probability, you can get, we'll see that probabilistic mechanisms are very important, and we may talk about getting a certain good with a certain probability. Now, completely equivalently thinking, instead of getting a certain good that is worth for me 100 with probability half, I get, if any quantity of the good I can get half the good, and it's worth for me half of the 100. So my valuation of fractions of the good is linear in the fraction. Okay? Very good. Now, the seller has no valuation for the goods. They are worth for him nothing. He just wants to sell them, and no cost, nothing. Again, one can have values, cost, whatever. Those are simple complications. Again, we want to maximize the revenue. Okay? So let's start with one good. Okay? One good. For one good, the problem is solved. Okay? Meyerson, 1981, and there was also Riley Samuelson, I think Riley and Zeckhauser maybe.
That was even earlier.
There was even earlier. I don't know. It says 83 when I looked at it. Probably it was published earlier. I don't know. So everybody calls it the Meyerson result because Meyerson has it very clean, but other people at the same time got it. And here is the one good result. The one good result says here is an optimal mechanism. Now, when I say optimal mechanism, I always mean mechanism that maximizes the revenue of the seller. Okay? So here is an optimal mechanism. He posts the price P and gives to the buyer two options. Take it or leave it. You can pay P and get the good, or you can pay nothing and get nothing. You choose. Okay? Can't be much simpler than that. That's what I always do when I go to the store. Yes? We pay the price and take the good, or we don't take the good. Okay? Now, how is P chosen? P is chosen in such a way that the revenue is maximized. Since the buyer is going to take the good if and only if his valuation is above the price, and again, greater or greater equal, I don't care much, then this is the probability that he's going to buy, and he's going to pay every time that he buys the price that he's been asked P, so the revenue is P times the probability that there's going to be a sale. So far so good? Okay. And so, puns at the end. Okay, only except for the speaker. He's allowed to make as many puns as he wants. Okay, so that's P times 1 minus f of P. Oh, I see that my script f became a regular f, but never mind. That's a cumulative distribution, and we just maximize that. Okay? By the way, if you try to prove it in class, you realize that's a non-trivial result. Okay? In fact, I'll give you a proof a little later. It's not at all trivial, okay, to prove it. That's a revenue of x. Okay, I'm going to denote it's a revenue of x. Now I want to say parentheses. I said I'm going to take the simplest model. If you just add a little risk aversion, either on the seller or on the buyer side, then Thomas Zidner, who was a PhD student here, has a nice paper that characterizes this result, and turns out it becomes infinitely more complex. Rather than a single price, you have a continuum of prices. Already a small multiplication from risk neutrality to some risk aversion on either side of the market. It's unfortunately never been published, but you can find it on my webpage, so you have the link. Okay, let's take an example. Okay, I like examples. So here is x, with probability 1/2, value 10, with probability 1/2, value 22. I'm starting slowly, okay? So I'm going to get faster as time goes by, but so bear with me, but I want everybody to follow everything. Okay, so now, what can be the price? Well, you can put a price of 15 or 15.725. Now, clearly, you are going to sell at the price 15, if and only if you are going to sell. I mean, clearly the 10 guy is not going to buy for 15, okay? So then it makes sense to put its price either 10 or 22. Again, let's ignore the tie breaking. When you are indifferent, let's assume that when the buyer is indifferent, he buys. If not, you put the price, 10 minus epsilon. The epsilon doesn't matter, okay? So if the price is 10, then with probability 1, there's going to be a sale, and the revenue of the buyer or the seller is 10. If he puts price 22, only when the buyer has valuation 22 is going to buy, and so you get 22 is probability half, which is 11. And as far as I know, 11 is bigger than 10, so maximum revenue, 11. Price, 22. Okay? Very good. That's one good. Okay, now let's do two goods. That's 3, 4, and so on. So let's do two goods. So now I have two goods, and let's assume they are independent. What do we mean by independent? The valuation of the first good is independent than the valuation of the second good. The fact that I know something about how much the first good is worth to me as buyer, or sorry, that's what the seller thinks. Any knowledge on how much the first good is worth to the buyer tells us nothing about how much the second good is worth to the buyer. Those are completely independent. So we are going to put a price P1 for good 1 and price P2 for good 2. Okay? So let's do an example. X1 and X2 are independent. Same IID, independent identical distribution. And again, remember from the previous slide that the optimal price for good 1 is 22, and then you sell with probability half and get 11. And for good 2, you get 11. Right? So total revenue is 22. Right? Now you should learn, every time I say right means it's wrong. Okay? That's one thing you should learn. Every time I say right and everybody does like this, false. Okay? Here is another alternative. I take the two goods, make a bundle, put a nice ribbon around it, and say, you cannot get this good separately. You either buy both of them or nothing. And the price is 32. Why 32? Because 32 is 10 plus 22. So if I say you either buy the bundle or nothing, the bundle for 32, when is the buyer going to buy? The buyer is going to buy if the buyer is not going to buy if both goods are worth 10. In all the other cases, the valuation is 10 plus 22 or 22 plus 22, which is more than 32. So we are going to have a probability of 3/4 of a sale. 32 times 3/4 is 24. I checked the numbers, believe me, it's correct. Okay? Okay? 24 is bigger than 22. Okay? So that's a place where we start scratching our head. What's going on? Okay? Something here we don't understand. I mean, come on, the goods are independent. How come suddenly I put a ribbon around them, I can get a higher revenue? Okay? And I can tell you that, everybody that hears this gets hooked. Okay? My co-author, Noam, yes, I remember, was upstairs after one of the seminars. I told him about that, and that's it. That's how he got into this. And he's still stuck here, for 20 years. Hasn't succeeded getting out of this problem. So it's quite amazing. Okay? Okay, now, before I tell, so that already tells us that something interesting is going on when you have more than one good. Okay? So before telling you, let's try to think about the general model. So what's a general mechanism? Okay? Now, a general mechanism, of course, is I can start talking with Eric, I can talk to, anybody here, I can start dancing on one foot, I can say, give me 10 and some flowers, I don't know, I can do whatever. But at the end of the day, there's going to be an outcome, okay? The outcome is what? The outcome is characterized by two things, or by a number of things. One, what is the probability that the buyer gets good I? For I equals 1 to k. We have k goods. 2, so those probabilities are numbers between 0 and 1. And remember, in our very simple model, each qi is between 0 and 1. They don't add up to 1, because I can get good 1 and I can get good 2. Parentheses, you can work with other sets of allocations, like summation qi equals 1, same problems. But we focus on this for now. And the other thing is the payment that the buyer has to give the seller for the goods, which I call S. Okay? Now the reason for this notation, S is what the seller gets. And now we're asking, what does the buyer get? What is the payoff of the buyer? The payoff of the buyer is what? He gets good 1 that is worth to him x1 with probability q1. Remember, everything is linear in probabilities, so gets X1 is probability Q1, Xk is probability Qk, and you subtract S, which is how much he has to pay because of quasi-linearity, and B is the payoff of the buyer. Okay? Now, everybody in this field uses a different notation for this, and for 1 year I was completely confused, and every time I said, wait, that's a buyer, that's a seller, that's a payment, transfer, revenue. So, for now on, in this lecture and in my papers, B is the utility of the buyer, S is the utility of the seller. And there is no, believe me, I stopped being confused at that point. I have not succeeded in convincing other people, except my co-authors who had no choice, of course, to follow my rule. But other people, I think, maybe some of my students, I don't know. Yanai use B and S, I don't know. Or you went to and you...
I
okay,
know how
don't
to
answer,
read
don't
BNS.
answer, don't
I
answer.
know how to read BNS. Since you asked me, I will say that it's not entirely true that everyone else uses different notations. Everyone else uses a different notation.
Yeah. No, you are, okay, let's not argue that you are wrong. Okay, anyway, so B is the final payoff of the buyer, S is the final payoff of the seller, and the seller just gets it because the buyer transfers to him. The buyer gets something from the goods, from which you subtract S. Okay? You can write it as scalar product Q times X minus S. Okay. Now let's talk about very simple mechanisms, which are, yes?
But when, can you go back slightly? But when you're talking about outcomes here, are we necessarily assuming independence in this?
No, because we are taking expectation. And the expectation of x1 plus x2 is expectation x1 plus expectation x2, whether or not x1 and x2 are independent.
No, that's
Isn't
true,
that beautiful?
That's true when we're talking about the buyer and the seller outcomes,
Yeah.
because we're assuming.
That's all we care. That's all we care.
No, but just the outcome could be.
I know, but I only care about the expected payment. And for expectation, that's the beauty. I don't care about the correlation. That's, again, it's a surprising result in probability theory, you know, that when x1 and x2 are correlated, still the expectation is the sum of the expectations. What can you do? That's life. But it's surprising. Okay. Good. So let's talk about a very simple mechanism. What's a simple mechanism? And remember, something a la the take it or leave it pricing mechanism. Okay? So now it's going to be that the seller tells to the buyer, here's a set of possible outcomes. What's an outcome? An outcome consists of a set of probabilities of getting the various objects and the payment. So it's in 0, 1 to the k times half. That's an outcome, right? Okay? And the seller says, here is a menu. What's a menu? Well, you go in a restaurant, you get a menu, you choose from the menu. The only thing is that you can only choose one thing from the menu. So this is the menu, what's called, you know, in restaurants you have menus. So the menu consists of menu A, menu B, menu C, and you have to choose one of the three. Yeah? So those are already well-defined combinations of things. Okay? So the seller posts a menu, and the buyer chooses one outcome in the menu, whatever he wants. Okay? And let's denote the outcome chosen by the buyer when his valuation is small x, q sub x, s sub x, in some element in the menu. Okay? What does the seller get? S of x. What does the buyer get? Well, b of x, which is qx times x minus sx. It's previous slide, nothing new. Okay? So let's call this a menu mechanism. Okay? Now here comes a nice result, directly from Mount Sinai, the revelation principle. I mean, it's a triviality. Okay? It's called the revelation principle. Everybody thinks that, you know, they saw something. It's a complete triviality. It says, take any mechanism. Think of it as an extensive forward game. You don't care what's going on. What you care is, at the end, there is an outcome. That's it. That's all you care. So, the revelation principle says every mechanism is equivalent to such a simple menu mechanism. And as I said, it's a complete triviality. Okay? But it's a very powerful tool. Because it says we don't have to think about mechanisms. I talk to him, I send him this offer, I counter offer, so on. We only have to look at the menu, choice after the menu. We only look at direct mechanisms. Direct mechanisms specify for every valuation qx and sx. Okay? So that helps us. Okay, now what are the equilibrium conditions in this game? Okay? For the buyer, we have what's called the incentive compatibility conditions, as we saw in the previous lecture as well, which says, look, if your valuation is x, that's what you get. But you could pretend that your valuation is y and take whatever y is getting, another different valuation. Then you get the good one, which is worse to him, x1, with probability q1 of y, because we're pretending to be y. And you pay s of y. If that thing, if the reverse inequality would hold, that means that when you are x, you pretend to be y, you'll get a higher payoff. That can't happen in equilibrium, so we must have this inequality. That's called incentive compatibility. And there is also a participation constraint saying you can always get 0. You can always not participate. Okay? Nobody can force you to participate, which says that the payoff is at least 0. Okay. Now, seller wants to maximize revenue, so now we can, very easy now to write the problem. What's the revenue? You look at S of x. X is a random variable. S of x is a random, real random. X is a random vector in RK. S of x is S of x as a random variable. You take the expectation. And for those like Noam who don't understand expectation, like integrals, that's the integral. Or the other way around. Yeah. Okay? Subject to what? Q and S, this pair, those are now functions that for every small x associate Q of x and S of x, should satisfy the previous slide constraints, IC and IR. Okay? Very simple problem. Okay? Okay? Now, let's look a little at the incentive compatibility constraints. And I claim that the function b, should be a surprise if you listened well to the previous lecture, that the function b is a convex function of the valuation. Okay, why is that? Because for every y, look at this expression, qy times x minus sy. As a function of x for fixed y is a linear function in y. Well, more precise, affine. Linear means that it goes to 0. But everybody calls it linear. It's a linear function of x. It's a constant times x, constant vector times x minus sy. Now what is bx? It's just the maximum of those of all possible y's. So maximum of linear functions, maximum of linear functions is convex. End of story. Okay? But we get more. bx is qx times x minus sx. That's what we said. Okay? Now, first order conditions, envelope theorem, I don't know what sensitivity, whatever, I don't know where you come from. When you solve this maximization problem, I claim that q of x must be exactly the gradient of bx. Think about it. Suppose that x1, the valuation of good 1 increases by epsilon. Okay? Now, if everything is nice, then essentially, if the change in valuation is small, you are still going to use the same q and s. So what's going to happen to how much the buyer gets? He is still going to get x1 with the same probability as before, but he now gets an extra epsilon. So he gets epsilon times q1 of x, which is the probability of getting good y. So that means if I increase x1 by epsilon, my payoff increases by epsilon times q1 of x. Divide by epsilon says that the derivative of b of x with respect to an increase in x1 is exactly q1 of x. Did anyone follow? No. You have to go to, differential calculus minus 001, I don't know. But thinking this way, okay. No, you take derivatives, okay? So, b is a convex function. Now, convex functions are nice. They are differentiable almost everywhere. So, so what we have, the qi of x is the derivative of b with respect to xi. If you increase xi by little, it's exactly the probability of getting good i. That gives us quite a lot. Okay? Okay, and then once I know what this is, I know what s is. Because what is s? Is qx times x minus bx. So I get a nice formula. Okay? Let's put it here. Here is our problem restated. We have to look at all functions, which I call b script bk. Those are all functions defined on RK plus, non-negative, that are convex. Okay? Their derivatives are between 0 and 1. Why? Because we want qi to be a probability. So it has to be between 0 and 1. We want b of 0 to be 0. That's just a convenient normalization. Let's not get into that. And then, what is the revenue that you get? Well, it's just the expectation of s of x. Remember what s of x was? The gradient of b at x times x minus bx. Okay? And it's defined almost everywhere. You can also write it as directional derivative, never mind. Anyway, revenue of x is, you have this expression here, for every function b that is convex and gradient between 0 and 1, which says 1 Lipschitz with respect to the L1 norm, by the way. Those that like to hear bombastic words. And that's what we want to do. Okay? Now, the function bk is a nice convex set. Average of convex functions are convex. Average of functions whose derivative is between 0 and 1 has derivative which is an average between 0 and 1. Okay? Average of functions that are 0 and 0 is 0 and 0. So this is a convex set. It's also closed. I mean, limits of such things stay there. That's easy to see. All the conditions are point-wise conditions which here are satisfied in the limit. So if we maximum, okay, sorry. What about this expression? This expression is a function of the function b is linear in b, which means if I take now a b1 and b2, two functions in that space, and look at what is written here, not for b, which is half b1 and half plus half b2. Well, this is half b1 plus half b2. The gradient of half b1 plus half b2 is half the gradient of b1 plus half the gradient of b2. So this whole expression becomes exactly half the expression for b1 plus half the expression for b2. So you have a linear functional on the functions b. Since b is a closed convex set, well, there is some compactness here, but never mind. What it says, they should look at the extreme points. Okay? You maximize the linear function over a nice convex set, then you know that the maximum is at an extreme point. So we just have to find extreme points. Easy problem, right? So let me show this. That, by the way, Manelli and Vincent. Again, I'm not sure I'm giving enough references to everything. I mean, the literature is huge. I mean, I can, for 2 hours, just put slides with papers. Okay, so let's take one good. For one good, we have functions, okay, convex functions on R plus. Start at 0, convex. Okay, that's a convex function, increasing. Derivative is always between 0 and 1. The slope never goes above 1. Okay, so those are functions whose b, real functions, whose derivative is always between 0 and 1. Okay, and I'm computing b prime x times x minus bx. Okay, now here is a nice result. What are the extreme points? What are extreme points of this? Those are functions. So again, those are functions. Again, you start at 0, derivative increases all the time because it's convex. Convex means derivative goes up. You start at 0, derivative is always between 0 and 1. So extreme means derivative is 0 or 1. Clearly, it cannot be first 1 and then 0 because it has to go up. So derivative is 0 and then 1. 0 and then 1. How does such a function look like? Well, if it's 0 up to 100, and after 100 it's 1, it's the function which is the maximum of x minus 100 and 0. X minus 100 and 0. So it's a function called b sub p. For p equals 100, I just told you what this function is. And a neat exercise, trivia. Every function in b1 can be expressed as an integral, as a convex combination of such functions. Many infinitely many, of course. Okay? An integral of alpha p bp. That's quite easy. Okay? But a neat exercise, which means I don't have to look at all the functions in b1. It's enough to look at these extreme ones, right? Because I'm maximizing a linear functional. Now, for such a function, what is b prime of p of x? Well, this is going to be non-zero only provided x is bigger than p. And then the derivative is 1. So I get 1 times x minus, this is the function x minus p. So I get exactly the formula that is so p times the probability of x bigger than p. End of proof. Neat proof, huh? Okay? As I said, but you have to work on it. So we got back the Myerson, etc. result. Okay? Okay. K equals 2, or more than 2. Okay? Remember again, we want to look at all the functions. Now, I have 2 dimensions. Start at 0. I have a function that is convex. And derivative never go above 1. It goes between 0 and 1. So you just have to characterize the extreme points. Couldn't be so difficult. In fact, it's extremely difficult problem. Okay? I mean, I remember Roger, in fact, I remember visiting Roger in the 80s, yes, and remember, he asked me this question. He said, oh, what's the problem? What's the problem? You know, I started thinking, of course, I didn't get anywhere, yeah. So It's really as easy as the problem for k equals 1 is, so complicated, it's 1 over the easiness for k equals 1. It's infinitely complicated. There is no useful characterization besides saying the extreme points off. Okay? They can be as wide as you want them. And if you look in the Manelli and Vincent papers, I have 2 papers. In the second one, they just talk about the extreme points, and you'll see examples of very crazy functions. You'll never in your life think of such functions, for sure not that those are extreme. Okay? Okay, so let's see what we can do. Okay, so let's go back to a few examples. I'm going now, that was some formal, and we'll go back to it, but let's look at some examples. So suppose that y and z are our friends from before, 10, 22. I just want to remind you, assume that y and z are independent and identically distributed, and both of them get 10 and 22 with probability half-half. Then, if you remember, if we set them separately, we get 11 apiece. Why do we get 11 apiece? Because we put price 22, sell with probability half, get 11. So we get 22. If we sell them bundle, okay, wait a minute, how do we solve the bundle problem? Very easy, because bundle says we look at y plus z. So the value of the bundle is 20 with probability a quarter, 32 with probability half, and 44 with probability a quarter. I hope everybody followed that very complex thing. But it's a one-dimensional variable now, okay? And we can use the formula of p times 1 minus fp to solve it. So we either put price 20, or price and sell for sure, price 32, sell with probability 3/4, price 44, and sell with probability a quarter. The maximum of that is here, and that's 24. So it's not just that I claim it's a bundle, it's a solution of the one-dimensional problem of the bundle. Okay, very good. So solution of this problem, we have to put a price on the bundle. Very good. So problem solved. Example 2. 10 and 50 is probability half-half. I mean, it should be the same, right? So if I sell separately, what do we do? Well, either price 10 and then I get 10 for sure, or price 50 and then I get 50 with probability half, which is 25. Go for the 25, yes? So the total revenue when selling them separately is 25 apiece, which is 50. What if I bundle them? Well, if I bundle them, then the value is either 20, 10 plus 10, or 60, 10 plus 50, or 100, 50 plus 50. Here I sell with probability 1, here I sell with probability 3/4, here I sell with probability a quarter. That's 25, that's 45, that's 20. Maximum is 45. Again, the bundle. The 45 is less than 50. So I should not bundle. I should immediately take the ribbon off. So here, I should price each good. Now what's the difference? I mean, they are almost the same. I change the numbers a little, and suddenly, I should sell them separately rather than the bundle. Okay? It's, by the way, it's an interplay of probabilities and values here, which determines what is better.
Can you put again how you got 44?
60 times 3/4, right? And 100 times, you can check the computations. Let's put it this way. This example has been around for, 20 years? I don't know. Nobody had found an error in the multiplication, so I believe that's correct. Okay. Okay, so we price the goods or we price the bundles, okay? End of story. Come on. Example 3. Y and Z, again, are IID. Take the values 0, 1, and 2, equally probability, a third, a third, a third. If we sell them separately, I'm not going to go through the details. You have the slides, you can check them. You get 2/3, okay? Either at price 1 with separate probability 2/3, or price 2 with probability 1/3, that gives you 2/3. So selling separately, you get 4/3. Bundling, well, you have no more values, 0, 1, 2, 3, or 4, all possible sums of 2 such things, and you plug in the probabilities, and you get 4/3 again. So that's the best you can do. Well, as I said, very good, you learned it. Here's another thing, okay? And let me represent it as the easy way to represent it as the menu, as the buyer payoff function. What's a buyer payoff function? What does he maximize upon? Well, he can buy the first good for 2, he can buy the second good for 2, or he can buy both of them for 3. You have the menu consists of 3. Well, there is always the option of doing nothing, which I don't count because it's always there. There are 3 options. Pay 2 for the first good, pay 2 for the second good, or pay 3 for both of them. Choose one of these 3 options. That's the menu. Okay? If you compute here, you get 13 over 9. And the nice property of 13 over 9 is that it's 1/9 more than 12 over 9, which is 4/3. Okay? It's bigger. Okay? So the revenue here is by doing this thing, where you put a price, that's by the way the unique optimal mechanism. I'll tell you later how I know. So you have to put a price on each good and also a price on the bundle. Okay? Simple examples. Okay? Okay, end of story. Not yet. I still have time. No, I know, I'm only beginning. I'm just warming up. Okay. Let's look now at YZ. Now, let's not assume they're independent. Let's assume that there are 3 cases. Either I value good 1 at 1 and I don't care about the second, or I value the second good at 2 and I don't care about the first, or I value both of them at 3. 3 equally likely possibilities. Okay? Now, it turns out that the unique optimal mechanism is the following mechanism. Here are the choices for the buyer. You get 0, get nothing. Okay, that's easy. Ignore that for a moment. Pay 2 for the second good, pay 5 for both of them. Or pay a half for a half chance to get good 1. It's a lottery. I'm selling him a lottery ticket that says, pay me $50 and you get a 50% chance of getting good 1. Or if you want, you get half of good 1. Okay? Now you'd say, wait a minute, you are cheating. So the revenue of that is 2.5, by the way. You already told us that every B is an average of simpler B's, right? So we should be able, so if B, right, the set of functions B, so let's decompose this half x1 minus a half, we can decompose it into 2 things. One, I put x1 minus 1, and one I put 0, right? Half x1 minus a half is 1/2 of this and 1/2 of that, right? So let's do this decomposition. Then 0, x1 minus 1, x2 minus 2. Here I leave blank for a moment. And here I have 0, and again 0, x2 minus 2, and that. But wait a minute. Can I put here 5? No. Because suppose I want to take this 5 and put it here. What's going to happen? In this mechanism, the 3-3 guy, who is the only one that has chance of buying both goods, is going to say, wait a minute, for both goods, I have to pay 5. 3 plus 3 minus 5 is 1. But I can get the first good, which is worth for me 3 for 1. 3 minus 1 is 2. So if I put here 5, it's immediately going to go here. And I'm going to lose revenue. The only way for that not to happen, in parentheses, incentive compatibility says, here I have to lower the price at 4. Okay? So what happens now, if you look at the corrected mechanisms, both of those give you revenue of 2 1/3. So we have a mechanism where the function B is an average of 2 B's that have no randomization. For both of them, the revenue is lower. Because the linearity does not work on the menu level, does not work on taking an option and saying this option is half of that and half of that. It only works on the functional level, which is not what we are doing here. That says that we may have lotteries like this, and there is no way to get rid of them through the convex extreme point argument. I mean, it took some time, at least for me, to understand where we are going wrong, because we said it's extreme. If it's extreme, extreme does not imply that probabilities have to be either 0 or 1. Does not imply. Okay? So I said that's a unique optimal mechanism. Okay? If you want an IID example, it's the same. Okay, that's okay. So let's summarize the examples. When you maximize revenue for multiple goods, you can do various things. You can post a price for each good separately. You can post a price for the bundle. You can post price for each good separately and also for the bundle. Or you can post prices on lotteries, and that's crucial. Okay? 1 and 3 are deterministic mechanisms, and of course 4 is a stochastic, a probabilistic mechanism. Okay? if you want some discussion, I mean, this probabilistic thing is quite amazing. Again, doesn't appear in one good, only appears in two goods or more. My paper with Rennie on non-monotonicity, I'll talk later, has a section that discusses the need for randomization, tries to get really what's going on there. I think we'll try to understand it. Okay, very good. Now again, this is in, zillions of papers talk about it. That's not very good. Okay, now let's take a simple problem. Okay, simple problem. Let's assume that we have that x1 up to xk are uniformly distributed of 0, 1. Okay? Let's try to solve first some simple problems, and then we'll try to solve the general problem. Okay? So IID. Okay? So for k equals 1, it's very simple. I have one good whose value is uniform between 0 and 1. The price that I'm going to put, so it's p times the probability of being above p, which is 1 minus p. So I maximize p times 1 minus p. Anyone follows? That's p equals a half. Very good. Okay? Now, I want you to do in your head, what's the solution for two goods, both of them uniform on 0, 1? Well, here is a solution. That's a unique optimal mechanism. You can get either good, xi means x1, or you can get either good for 2/3. Or you can get both of them for this very rational number, 4 minus square root 2 over 3. That is the unique optimal mechanism. Okay? Phil and I worked it out. Other people did it also, yes, exactly, not approximately. 3 pages of lemmas and things and so on to solve it. Okay? K equals 3. Let's continue. We are on a roll. Okay? You pay 3/4 for each good separately. You pay 6 minus square root 2 over 4 for 2 goods, and you pay S for 3 goods. What is S? This is S. You cannot argue with that. Yes? That's how much you have to pay. That is the unique solution of this very simple problem. Yes? You maximize revenue, you have 3 goods, each one is uniform distributed on 0, 1. Okay? Now, if you're wondering what this is, well, I wrote it in one of the complex ways one can write it, but that's a solution of a third-degree equation whose coefficients are in q square root 2, rationalizing and square root 2. Okay? A third degree, you get a third-degree equation. Okay? And that's it. Okay? You can continue. There is, in fact, a nice paper by Giannakopoulos, not John. This is Giannakopoulos, okay, and Koutsoupias, that does it up to k equals 6. And it's not that they gave up at 6. Their method does not work beyond 6. Okay? I also tried, and we tried to look at it. It's a very difficult problem. Okay?
It would work for, already for 6, they need like 10 pages. For 7, they would need 30 pages.
No. There is no. There is a problem there. By the way, there is a lemma there that is false in the paper, but that doesn't affect the result.
You might have been able to squeeze 7 out of it.
Okay. I have a conjecture. I know what the solution of the problem is. Okay, I think I know, and that fits. That fits everything that is known up to 6. Okay. Okay. Monotonicity. Right. Monotonicity was discussed in the previous lecture. So here, what's monotonicity? Monotonicity is the following phenomenon. Suppose that the buyer is willing to pay more for the goods. His valuations for the goods go up. His willingness to pay goes up. Now, that means that the seller should be able to extract more, so maximum revenue increases. Okay? So let's prove it. No, let's prove it. You be quiet. Okay? Let's prove it. Okay? K equals 1. We'll start with K equals 1 as usual. So let's take y bigger than x. Okay? Those are real numbers. Yes? K equals 1. Here is the incentive constraint that when you are at x, you don't want to go to y. Right? Qx times x minus sx is bigger than qy times x minus sy. Right? Let's write down also the incentive constraint at y not wanting to go to x. Okay? Qy times y minus sy is greater or equal to qx times y minus sx. Right? Let's add them up. All the s's cancel, and you get qy times y minus qy times x, I put it on this side, greater or equal than qx times y minus qx times x. You follow the algebra? very complex. I mean, I'm showing you only the extremely trivial things, nothing of that, okay? Since y was assumed to be bigger than x, I can divide without changing the direction of the inequality. One better check that. So qy is bigger than qx. So that means a higher valuation is going to get the good with a higher probability. Makes sense? Could call this allocation monotonicity. From that we get, what is sy minus sx? Just from this equation, sy minus sx is greater than qyx minus qxx. So since this is bigger than this, and x is positive, then this is bigger than this. Okay, so what we got that for every y bigger than x, sy is greater or equal sx. So at an IC, and I only used IC, at any IC mechanism, the payoff function, what the buyer pays to the seller, is non-decreasing in the valuation. A higher valuation is paying more. Okay, very good. That says that if I take the buyer valuations and increase them, for every mechanism, for every fixed mechanism, the revenue goes up because I replace an x by a higher y. So the revenue for every fixed mechanism goes up. The maximum overall mechanism here, therefore, is less or equal than the maximum overall mechanism here. So the revenue is increasing when I go from x to higher valuations. Okay? In parentheses, working with random variables is nice because I can do it pointwise. If you want to think as first order stochastic dominance, be my guest. Sounds much more convincing when you say first order stochastic dominance, but that means in one dimension or in any dimension, that just means that pointwise you take valuations and move them up. Much easier to think this way. But first order stochastic dominance, revenue is monotonic with respect to first order stochastic dominance in the buyer valuations. Very good. K bigger than 1. I mean, should be a similar proof. Okay? But before that, let me show you an example. Here is a mechanism. Again, the way you read it, here are the options. 0, $10 for good 1, $20 for good 2, $40 for both of them. So you can take the plane, okay, x1, x2, and look in each region, every x1, x2, what is he going to choose? And this is the picture. In this area, you choose 0. The buyer chooses 0. Here, when x1 is very large, he chooses x1 minus 10. When x2 is large, he chooses x2 minus 20. And when both are large, he chooses x1 plus x2 minus 40. And you just solve, you know, when is this greater or equal than this and this and that, you know, a bunch of linear inequalities, and you do it 5 times just to make sure that you made no mistake, or, you know, plug it in Maple or whatever, and you get this nice picture, okay? So that tells you for every evaluation is a dot here, okay, an x1, x2. So every evaluation here is going to choose 0, which means that the seller gets 0. Everyone here chooses 20. But notice something interesting. Look at the green dot. The green dot pays 20. That's the optimal choice for the green valuation. Look at the red dot. The optimal choice for the red valuation is x1 minus 10 to pay 10. So what has happened is we move from, say, 2023, the green dot, to 2027, the red dot. Here, the choice was x2 minus 20. Now the choice is x1 minus 10. So valuation of both goods went up, but in this mechanism, now, instead of buying the second good for 20, he buys the first good for 10, which the seller does not like. He loses 10 from this guy. Now you'd say, okay, I mean, of course, I mean, that if you think a little about this, it's not surprising at all. The fact that there is a mechanism that is non-monotonic, so what? Yes, because you are always comparing how much you are gaining from one good to how much you are gaining from another good, and so this kind of phenomenon is standard. Question, can this be an optimal mechanism for some valuation? Okay? That's now a difficult question. Okay? Answer is yes. There is a valuation X for which this is the optimal mechanism. Not only that, it's a unique optimal mechanism. Moreover, it's a unique optimal mechanism even if you perturb it a little. It's strictly optimal. It's much bigger than anything else, strictly bigger than every other mechanism. I'll show you in a moment what this valuation is. What does this imply? It implies that if we perturb the X a little in the direction where we increase the valuations, and we take an x that sits on a place where there is no motonicity, you know what? Why do I talk? Here is x, okay? Forget that picture. This is the random variable, okay? And what we do is we take mass from here to here. As we take mass from here to here, so for this, with probabilities, let's say, probabilities 1/4, or 1/3, 1/3, 1/3 also works, okay? Probability 1/3 on this point, 1/3 on this point, 1/3 on this point. This is the unique optimal mechanism. Now, you have to prove that. Duality and so on, yes, but it's provable. Now what I'm going to do is I'm going to take some of this guy here and move it here. If I do a small enough change, now small enough turns out up to a probability of 1/12, not small like epsilon, 1/12, okay? Then this still remains the optimal, the unique optimal mechanism, but now the revenue has gone down from 20 to 10. Okay? So here, if you want to see, that's the x alpha, and the revenue, notice what alpha is. Alpha is how much mass moves from 020 to 2020. How much mass moves from red to green, from green to red, sorry. Okay? When you move this mass, you increase valuations and decrease revenue S. Okay? And the revenue indeed goes down as alpha. Okay? So that is, so again, by the way, that's a beautiful example of, I don't want to say on computer. This example was found by running Maple for a week. On random examples, just looking, I don't know, I mean, look, it was not an optimal program, maybe for 3 days, I don't know. It was running for some time, but just generate, I mean, at that point in fact, I think Noam and I had at least 3 different proofs that for k equals 2, you have monotonicity, right? If I remember. Every time, we just needed a small lemma, okay? We just needed a small lemma. After 1 year that we couldn't get yet another lemma, we started thinking, well, maybe that's not true. So then I started talking with Phil, and I wrote a Maple program that started, 3 by 3 examples or something. Just generate random examples, compute. Now, to compute, if you are given an x that has finitely many values, computing the optimal mechanism is a linear programming problem. It's maximizing a linear function subject to linear constraints. So, you run simplex. And you just run it, okay? And trying to find the mechanism that is non-monotonic, okay? Now, we found an example that's very complicated, and then you start simplifying and simplifying, by the way. So, computer science has a role in economics.
So we can call it a weak result. Pun intended.
Okay. Okay, very good. Now, so this raises some questions, okay? This raises some important questions. If the valuations of the buyer go up, and the seller not only cannot profit from that, he's going to lose from that, okay? That's terrible, okay? So the first question is, how much can he lose? Well, he could lose 1/12 there, he could lose a little there, okay? Not much. So maybe one can put a bound on how much that loss is. Now, as I said, to find a non-monotonic mechanism that is optimal took a week of whatever time of Maple to find it. That means they are not lying around. Again, non-monotonic mechanism, that's very easy to write. I put down such a mechanism, okay? Non-monotonic mechanism that is optimal, uniquely optimal from some valuation, that's a tough problem, okay? As I said, it ran for a week until I found an example. That means they are quite rare, okay? That means that we don't expect this non-monotonicity to be a very serious problem, okay? Sometimes it happens, even this example is not pathologic, but sometimes it happens. The question is, how large can the loss in revenue be, okay? Answer, very large. I'll show it to you in the second half. Extremely large. In fact, you can lose all revenue, essentially, okay? You can lose all revenue. The valuations, so you have a certain revenue, and the valuations of the buyer will go up, and your revenue go down to an epsilon fraction of the revenue for every positive epsilon, okay? So that's a big problem. Now, think about it. Another way to look, oh, sorry, before that. What can the seller do against it? Can the seller do anything? Now, there are other non-monotonicities around, like, you add a buyer, then the profit of the seller goes down. So the seller solves it very easy. I add a buyer, I don't get offers from you, you're out. So, other non-monotonicities that exist in the area, the seller can easily overcome them. Okay? This, I have no idea how to do it. Okay? In fact, I claim there is no way to overcome it. So the buyer, moreover, if you look at the example, the buyer has an incentive. He gains by increasing his willingness to pay. He's willing to sign a contract saying, I'm willing to pay not 1 million, but 2 million. Now the seller optimizes, and in the end he gets more. Okay? What can the seller do? I don't know. If somebody will come up with a clever idea on how the seller can overcome this, the buyer is willing to pay more, and the seller gets less. That's life. Okay? Okay. Now, here's another question that arises here. Let's define G-rev of X to be the worst revenue that you get. So assume that X is not really the valuation of the buyer, but it's a lower bound on the valuation of the buyer. So I know when I say that he values the good at 1 million with probability half and 3 million with probability half, I'm thinking he values the good at 1 million or more with probability half. He values the good at 3 million or more with probability half, because I don't really know, yes? But I have some lower bounds. So this says, if everything were monotonic, I would do the following thing. I'll solve the problem for 1 million, 3 million, and then I say, well, if it's worth to him more, I can only get more. Very good. But now, I'm afraid that if I solve the problem for 1 million, 3 million, and this valuation is higher, in fact, I'm going to get much less. Okay? So the question is, how much less? So let's define G-rev to be the minimum of the revenue of Y for every Y that is bigger than X. First order stochastic dominance or inequality pointwise, whichever way you like. Okay? Here is a nice reason. Why do we call it G-rev? It's called G-rev, short for guaranteed rev. Why? Because it turns out that there exists a mechanism that the seller can use such that no matter what valuation Y the buyer has that is above X, the revenue that is going to get from that new Y is going to be at least that. So there is a way to guarantee, without knowing what Y will be, this G-rev, which is called guaranteed revenue. Okay? And by the way, the proof of that is the Minimax theorem. It takes some 3 pages because there are some technical issues there, but essentially the idea is Minimax, but you can guarantee it. Okay, very good. Okay, computer scientists, let's talk a little, one moment of complexity. In fact, you almost, I don't know, you saw my slides because you use words that you'll see in a moment here on my slide. So here's the problem. You want to maximize revenue. One buyer, one seller, 2 goods. Okay, very simple. Let's assume that each good has 10 possible valuations. It's not, equally probable, whatever. Solution of this problem, you solve a linear problem. How many unknowns you have? You have 300 unknowns. Why? Because you have 10 cells. Every combination of value of good 1 and value of good 2, it's 100 possibilities. For each one, you have to say what Q1 is, what Q2 is, what's the probability of getting good 1, what's the probability of getting good 2, what's the transfer, what's the payment. 3 numbers. So that's 300 numbers. Now, believe me, I've solved those things. You start with, I showed the examples with 1, 2, 4, but you do 1, 2, 7, and suddenly you start getting probabilities, so you're getting transfers of the form 10,272 divided by 100,000, some crazy numbers, okay? So you are going to get 300 numbers. They are not going to be 0 and 1s. You wish so. There are 300 numbers between 0 and 1. They are all rational if you started with rational numbers, but they are crazy, okay? You look at it, you have been hired as a consultant to tell how to sell this optimally. You come with these numbers and they are going to throw you from on the steps, right? I mean, what do you mean? I should price this at 2.77 times, remember the square root, remember the formula that had for 3, no, that's infinite, but still. We don't understand the structure of the solution, okay? We have, so what I claim we can solve it polynomially. It's polynomial. So computer scientists are happy. This is a polynomial problem, not NP. Polynomial, right? Linear programming, what could be nicer? But still, computational complexity that says this is polynomial, I claim does not capture the difficulty of this problem. Okay? Even after computing the precise solution, we don't understand what it means. Yes, we just get numbers, 300 numbers. What is this mechanism? I have no clue. I have no idea. What is it? Okay? It's not monotonic. It's not nothing. It's some crazy thing. It's optimal. Okay, very good. So what? Okay? So I propose, again, there was some computer science thing, I think at Microsoft, I don't remember. So I propose this thing called conceptual complexity. So that's something that goes beyond the computational complexity. It's not computational complexity. It's not communication complexity. It's another CC, conceptual complexity, which says even when you can get the precise solution, you are clueless about what you got. Okay, you don't understand the structure. It doesn't tell you what to do. It's not my solution, so what? Okay, so I claim that this problem of multiple goods is conceptually very, very complex, much beyond what the usual measures of computer science tell us.
You have a formatization?
No, at some point I thought about it, but no. You want to pick it up? I mean, you used almost the same words in your when you said. So okay, let's talk about it if you want to. You pick it up. Come on. Okay, there is something beyond that. Okay. In fact, I remember having an argument in our lounge with Christos about this. At the beginning, he was very against it, but then maybe there is something. But okay, I don't. Okay, so summary up to now. Maximizing revenue with multiple. So it's not summary of. It's summary of not of part A. Partial summary up to now. Okay, so many of the things that we understand for one good, like post the price, deterministic, not true for multiple goods. Monotonicity, not true. Computational, not true. Nothing. It's a very, very complex problem, even when I give you very simple distributions. Okay. So what we have learned from one good is too good to be true for two goods. Now you can understand the title of the talk. Okay. Okay. Our intuition, a lot of our intuition in this area comes from one good. One good, everything is good. Okay? When you go to two goods, all these things are no longer true. Okay? It's a different world. Okay. So now, Eric asked this question in the previous lecture, but that's clearly a natural question to ask. Okay, since solving this problem is tough, very difficult problem. Okay. Now I should say there have been some advances here. Some nice work of Daskalakis and his colleagues on duality and so on, but those are extremely tough mathematically and not really useful. As I said, you want to know a solution, run linear programming, but that really doesn't tell you what to do. So now let's do something else. Forget optimality, but require simplicity. We don't want to look at all possible mechanisms. Let's look at simple mechanisms. Maybe if we look at simple mechanisms, we are not far away from optimal. Then optimal is optimal, but if it's tough and it's hard for us to find it, but simple mechanisms are useful enough, then let's use simple mechanisms. And we give up optimality. We are approximately optimal. Okay? So let's take two IID goods. Okay? Let me give you now, I'll give you some results. Do I have time for, okay, let's try. Okay. So here is a first result. Suppose that x1 and x2 are independent and identically distributed. I have until 3:30, right? 3:30, okay. Suppose that x1 are independent and identically distributed. Then we have the following result. The revenue of x1 plus revenue of x2, that is what's called the separate revenue. That means selling them separately. Find the optimal price for x1, find the optimal price for x2, and sell them separately. Ignore what's going on. That guarantees you a fraction, e over e plus 1, which if you are wondering how much it is, it's 73% approximately, yes. Okay? Of the optimal revenue. So take any distribution that you want. Now you have two IID goods. two independent and goods that have that same distribution. You look how much you get by selling them separately, you get at least 73% of the optimal revenue that you may have no clue what it is. Okay? So let me state it, that's work with Noam. Let me state it slightly different. Since X1 and X2 have the same distribution, they have the same revenue. So that's twice, so selling separately is twice the revenue of X1. So here is a way to understand this. Take P star to be the optimal price for selling X1 or X2 for that matter, they are the same. So what's the optimal one good price? It's the one that maximizes this P star times 1 minus f of P star, right? That's the maximum price. Post this price, this one good price for both goods. Essentially saying, look, P star is the price. You can buy one good, you can buy two goods, each one at P star, or you can buy none. That's what Rev X1 plus Rev X2 is. Putting price P star on good 1 and putting price P star, the same one, on good 2. That just says putting P star, but you can buy as many goods as you want. Right? Like you go to the store, there is a price. And you know, those are IID, the quality of those boxes, they are IID. You don't know what's in the box. You know? You think you know what you are buying, but you know. Okay? So if you post the optimal one good price per unit, you get at least 73% of the optimal revenue. Okay? Now, we'd like 99.99%, of course, but that's wishful thinking, okay? In fact, turns out you can never get, okay, I'll tell you later how much, there is an upper bound, which is, I think, 78%. So we are pretty close to the best, but that will come later, okay? I just give you now a list of results, and I'll try to explain what's going on. Take two independent goods, but not with the same distribution, then this 73% goes down to a half. Okay, again, result in the same paper with Noam. In fact, that half was not tight, so Phil and I worked for a couple of years and succeeded in improving it to square root E over square root E plus 1, that's 62%. It's a 10-page proof, yes? It's not anything that you want to write home about. But you know, we were into it and we thought a little more and so on. In fact, if they are regular is the Meyerson condition that says that the virtual valuation is increasing relative to the real valuation. For those who know, x minus 1 minus big f of x divided by small f of x increases weekly. We only need the weekly version x. So you have this kind of goods, which again, many distributions satisfy that. Then we are going back to the 73%. As I said, that's yes, Hart and Rennie. Again, if you are interested, look there. I don't think anyone read that paper. It's really. It was, you know, every time we looked at it, we said, well, we almost did it. Then no. At some point, we decided to do it. Okay. Now, I want to. Okay, I think I have some time. Let me go back to the one-half theorem because that's the basis for most of this kind of approximations. And let me tell you, where does it come from? How do you get that? As I said, 1/2 is not optimal, but it's simple enough that I can explain. And I want to
By
explain.
the way, what if it's independent and regular? Do you get better?
Well, if independent, no, it is, everything is independent. Sorry. It's still under independent. All this is independent.
Okay.
All this is independent. Non-independent, second part. Okay? We are going to get to the second part and that's a different ballgame completely. We are now in the independent part. Okay? So this is independent and, oops, sorry.
Wait, so the 73% that you showed
Okay,
us
okay.
first-
Again, let's make some order.
Oh, that was
IID,
identical.
73%.
Okay, so I meant to ask a different question. What if it's identically distributed and regular?
Well, then you get 73% two ways.
No, okay. It's
As I said, you'll see in a moment that the upper bound is 78%.
Yeah, but I'm asking if you know if there is a separation for both identically and regular.
What do you mean a separation?
That it's better than either of these condition 11.
Is this tight, the 73%? Is this a-
No, I'm not asking if it's tight.
Look,
I'm asking.
for me, 73 to 78 is tight, okay? I'm sorry. I mean, working from 50 to 73% was so difficult that I'm not going to spend any effort in going from 73 to 74.5, okay?
Well, you
So
worked
70
hard to get from 50 to 62.
I know, but that was a challenge. But once, now 62, 73, okay. But now, since I know that the upper bound is 78, I mean, be my guest. Okay? Anybody that wants, I don't recommend it. But if you feel like you want a challenge, if you want a real challenge, go read don't read the paper. Just go and do it yourself. That's, no. Start reading papers, then you'll get lost. You have to think for yourself. Okay, that's what I usually do. But, okay, so I want to explain the 1/2 because it's a neat trick, okay? And that trick is in fact gave many results and then generalizable to other things. So I want to prove to you this theorem, okay? I'll prove it to you, okay? That if Y and Z are independent, then the separate revenue is greater or equal than 1/2 the revenue of them together, which, as I said again, I have no clue how much that is. I don't know, okay? Okay, so take,
You
take,
know that it's tight?
no, I already told you it's not,
It's not tight?
because I already have an improvement to 62%, so it can't be tight.
Okay.
Yeah, I'll make some order later, I'll put you in, not a table, but you'll see everything. But
With no further
it's a
assumption?
basic,
You had 62 with no further assumption.
with no further assumptions. With the same assumption as here, I can get 62, but 62 you need 10 pages. For this, I can do it in the remaining time here, which makes a difference, right, in terms of complexity. Okay. So, take an IC and IR mechanism, okay? So here is a very complex decomposition. This is the revenue I get from this mechanism, right? The expectation of S, Y, Z. And I wanted to split this into 2 parts, okay? Okay. So this is Y, this is Z, Y, Z, okay? I just divide it in 2 parts. Here, Y bigger than Z, here Z bigger than Y, okay? So I want to look at the revenue on each one of these 2 halves plane, okay? So it just says the expectation equals the expectation of that when Y is bigger than Z plus the expectation of that when Z is bigger than Y, and the diagonal I count it twice, but if it's less or equal, I don't care. Okay, now I claim that this thing, when I look in this area, I get at most twice the revenue of Y. I claim that here, I get an upper bound, I get less or equal twice the revenue of Y. What I get here, so again, any incentive compatible individual rational mechanism, when I look at the revenue I get here, it is bounded by twice the revenue of Y. Similarly, here the revenue is bounded by twice the revenue from Z. So in total, I get twice the revenue from Y plus twice the revenue from Z, right? When I add up, I get this inequality. So the revenue from both of them is less or equal than twice the revenue from Y plus twice the revenue from Z. That's true for every mechanism, therefore it's true when I do maximum. I mean, I'm saying trivialities, yes, I mean, I of course have to prove the claim, but modulo the claim is this. Now divide by 2. Okay? So far so good?
Yep.
Yeah? No, you look puzzled, okay. Okay, so that's a claim, yes, just, I'm just showing I'm not cheating, that's a claim, yes, I'm just raising it up now so you can see, okay? And here is the way to do it. Fix Z. Let's fix here a Z. And let's look, I'm now only in this region, okay? I want to look at this line. On the line where the second coordinate equals Z, or fixed small z, okay? And what I'm going to do, I have a given mechanism, given 2-dimensional mechanism. What I'm going to do, I'm going to generate from it a 1-dimensional mechanism in the following way. Instead of giving, I'm going to generate a one-dimensional mechanism for the good y. How? Instead of giving good z with probability q2 of z, I'm going to lower the payoff by how much you would get. I'm going to give you a monetary refund worth q2 times z. Okay? So that you would, so as a buyer you wouldn't care. What do you care if you get z with probability q2 or if you get payment decreased by that amount? So this is the definition of a new mechanism on y. The probability of getting y is, so I'm looking now at the point here. This is the point yz. So what's the probability of getting y? Well, it's q1 of y, what it was. What's the probability of getting good 2? You don't get good 2. This is only for y, yes? That was just to check that you follow. Okay. How much do you pay? Well, you pay what you paid before, minus this. That's a refund that you get because you didn't get the z good. Okay? So, from the point of view of the buyer, he's indifferent between the original thing that he got and what I'm giving him now. Now, what I claim is that this is an incentive-compatible and individual rational mechanism for good y. Okay? You have to check that because this was IC and IR originally, that said that when you are here, you don't want to go here. In particular, don't want to go here. The fact that from here you don't want to go here, or you don't want to go here, that's exactly incentive compatibility relative to the y code. So this is the rest. In fact, you are requiring less. You are now requiring only incentive compatibility moving horizontally. Okay? But because you had incentive compatibility in every direction, you have also horizontal. Okay? So that's an IC and IR for good y. I'm cheating a little, not exactly IR. You have to do some things may become negative here. You have to do some correction, but it's almost correct. Now, let's see. Now we have the following inequality. Look at how much payment the original mechanism extracted from YZ. Well, take this formula and rewrite it here. It's what you got from the new mechanism for Y plus plus the refund. Yes? You see it's the same formula? Okay. Now, I don't know how much Q2 is. It can never be more than 1. So it's less or equal than SY plus Z. Okay? Very good. So I think it goes up because I have to continue, but it's almost done. Okay? Now, this is pointwise. This is the pointwise inequality. Okay? Take expectation. Okay? Expectation of SYZ, less or equal to the expectation of S tilde Y, plus the expectation of Z, everything in the region, everything here. Okay? On this line. In the region where Y is greater than Z. Then small z is fixed, 7. Okay? Think of small z equals 7. Okay? I just take that pointwise and take expectation. Very good. Now, this is a mechanism for Y. And I don't even look at all possible values of Y, only values that are bigger than 7. That's clearly not going to exceed the maximum revenue you can obtain from Y. What is this? This is the expectation of Z times the fact that Y is bigger than Z. That's just small z, which is a constant, 7, times the probability of being above Z. Okay? Do you recognize this thing? If I were to write instead of Z small p, would you recognize it? That's exactly the milestone formula that you maximize when you compute revenue. So that's less or equal than the revenue of Y. Okay? So what we got that this is less or equal than twice the revenue of Y. Now that's true for every Z. So that's true when you take expectation over Z, and I got my inequality here. Okay? Deceptively simple, yes?
Where did you use independence here?
I use independence, very good question. Because when I take the distribution of Y on this line, which is conditional on the value of Z equals Z, it's the same as the distribution of Y. If I didn't have independence, then I should look here at the revenue I get from Y conditional on Z. But because Y and Z are independent, the distribution of Y on this line, or on this line, or on this line, they're all the same. They have the distribution of Y. That's why it only works on independence. Okay, very good question. So I should have mentioned it. Again, it's a few years ago. I have to remember it, but still, I think I could Noam, you have any comments? No? You followed? Okay. Okay. I think. Look. No. I think I want to finish this a little early because I think it was enough material for now. And now I'm going to get to something else.
G4.
G4, which for economists, it's the better half of G8. Okay, questions? Questions? Anybody follow something? I don't know. It's not clear. Yeah,
More than two things.
more than two goods. Will come. Are you coming to the second half? I promise to talk about more than two goods. Okay? In fact, let me already say, Noam and I have been working for the last year or so, and a tentative title for the paper, won't be the title of the paper, it's Too Good to Be Three. Namely, too good is complex, still beautiful. You can get beautiful things. Three goods is infinitely more complex than two. I mean, for two goods, you can still have a lot of nice things that break down for three. Okay? So,
Maybe
But-
at 4 you become simpler.
yeah, who knows? Who knows? Before 4.
Is that what G4 means? Good 4?
Yeah, yeah. Okay, any other questions? Okay, coffee.